It's my pleasure to welcome everyone back to another season of the virtual AMO seminar, or VAMOS. A couple of quick announcements. So VAMOS is now a part of DAMOP. So we'd like to thank the APS and DAMOP for supporting VAMOS and for sort of taking us into DAMOP so that we can keep this going longer term. We're kind of trying to put it on a more permanent footing. And as a result of that, there are a few changes. So we have a new panel, and we'd like to first of all thank the old panel and VAMOS board for all of their service and everything they did helping organize and host over the past throughout the pandemic. And also want to welcome all the new panel members. I won't list everyone, but you can see everyone, and you can also find a complete list of our current and former board members on our website. The only other big change is that we're switching from being a weekly seminar to a bi-weekly seminar. This is sort of to reflect partially the fact that there's starting to be at a lot of institutions some in-person colloquia and seminars coming back, and so just not to tire everybody out and overload everybody, we thought it made sense to reduce the frequency a little bit. And so the next VAMOS will be in 2 weeks. You can find our full schedule on our website, and we'll also advertise the upcoming talk at the end of the seminar. Okay, so having said all that, it's my real pleasure to introduce Bill Phillips, who I think it's fair to say is one of the founders of modern AMO physics. You know, Bill is also a VAMOS regular, and so we thought it was appropriate for him to give the first seminar now that we're returning from our break. Bill did his PhD at MIT with Dan Klepner, and I'm not sure if Dan Klepner's in the audience or not. I saw that he'd registered. So I think all the grad students watching can relate to the experience of giving a talk with your PhD advisor in the audience. So let's at least try to give Bill our moral support. Bill is best known for his work on laser cooling, including the first magnetic trapping of neutral atoms, the first measurements of sub-Doppler cooling, and the invention and first demonstration of the Zeeman slower. I actually learned yesterday from Bill that the Zeeman slower was almost called the Phillips Metcalf cooler, but this apparently sounded a little bit too much like a refreshing alcoholic beverage. So we wound up with Zeeman slower instead. As a result of his many seminal contributions to AMO, Bill has received far too many honors and awards to list here, including, and I hope I'm pronouncing this right, the Nobel Prize, I think. I'm not sure, I think it's Swedish, but I hear it's pretty prestigious. So while Bill is best known in our community for his work on laser cooling, in his misspent youth, and those are his words, not mine, he also worked on electrical measurements, including early development of what has now become the Watt balance, which is an integral part of the new SI, and we'll hear about that today. So the last thing I'll say before I turn it over is that Bill is also famous in the AMO community for asking many insightful questions at conferences and seminars. One of the things I'm personally proudest of with VAMOS is that it has given a new generation of AMO physicists around the world the opportunity to hear a question from Bill Phillips and think, oh yeah, I was confused about that too, but I didn't even realize it. So today is our chance to return the favor. Please ask Bill questions using the Zoom webinar Q&A feature or via the YouTube chat. And also, if you're a student especially or a postdoc, please be sure to attend the post-seminar discussion with Bill, and we will post links for that at the end of the seminar. And so with that, Bill, please take it away.
Thanks very much for that, that kind introduction. And members of the panel, please interrupt me if something is going wrong, because sometimes things do go wrong in these video chats. Well, anyway, I'm from a place called the Joint Quantum Institute, which is joint between NIST and the University of Maryland. And I'm part of the Laser Cooling and Trapping Group. And Gretchen Campbell, Paulette Trey Porto, Ian Spielman, Ida Tietzinger, Charles Clark, and maybe in another few days, Nicole Younger-Halpern will be joining our group officially. So we do pretty much what the name says, but that's not what I'm going to be talking to you about today. But I am going to be talking about things that are very much AMO related, even though this is a talk about metrology and units. And because of that time as my ill-spent youth, I've become involved in promoting the new SI. So as a member of the International Union of Pure and Applied Physics, the Commission C2, which has responsibility for this sort of things, I'm trying to spread the word worldwide. So I'm claiming that there has been a revolutionary reform of the international system of units, what we call the modern metric system. So what is that revolutionary reform? Well, the French Revolution brought us the metric system in the first place. And on the 20th of May, which I'm sure you all know is World Metrology Day of 2019, we've experienced what I'm claiming is the greatest revolution in measurement since the French Revolution. And the nature of that revolution is a change to the international system of units, the specific definitions of 4 of the units, of the base units, the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela, form the basis for everything that we measure. 4 of those units have had their definitions changed just recently in 2019. And the nature of that change is that they are now defined by defining a fundamental constant of nature, or at least a constant of nature. Now, how is that possible? In order to see how it's possible and how it can be done, I'd like to tell you a little story, which I'm, with apologies to Stephen Hawking, calling A Brief History of Time, a little story about how the unit of time has evolved over time. So conventionally, we think of the unit of time as being the second, and the second is a day over 24 hours times 60 minutes per hour times 60 seconds per minute. So it's a day over 86,400. Now, that's great. And in fact, that was the official definition of the second, that it was this fraction of the mean solar day. Turns out that the solar day changes by a lot during the year. So it has to be with respect to the mean solar day. But since around the turn of the previous century, we have known that the length of the day changes for all sorts of reasons. The tides are constantly slowing the Earth down because of the friction. And in any case, there were clocks that could tell that, mechanical clocks, and then eventually quartz clocks that could tell that the Earth was changing its rotation. And so it became necessary to redefine what we mean by a second, because you had a technology that could tell that the old definition wasn't good, that it wasn't good enough for the kind of technology that we had. And so we had atomic clocks. The first atomic clock was actually not even an atomic clock, it was a molecular clock, but we tend to think of it as an atomic clock. The inversion transition in molecular ammonia was the first clock. Here's a picture of that first ammonia clock from about 1949. A little bit later, at the National Physical Laboratory, the equivalent of NIST in England, they made a cesium clock. There it is, 1955. But still in 1955, the definition of the second was based on the mean solar day. That's interesting. I don't seem to be advancing. Okay. And so it was necessary to change the definition. We'd known for more than half a century that the Earth was not a good standard, but finally in 1960, they changed the definition in the light of the fact that things like atomic clocks showed that the mean solar day wasn't constant. They changed the definition to be a fraction of the year 1900. What were they thinking? I mean, sure, the year 1900 never changes, but it's not exactly readily available for measurement. Now, astronomers are really good at extrapolating, and so they had a pretty good idea how long the year 1900 was, but it really was not the most convenient way of doing things. Finally, in 1967, they got around to adopting a new definition based on atomic time. And the definition is the same definition we use today, that the second is 9 billion and some cycles of the radiation corresponding to the hyperfine transition in cesium. So that's what a second is today. And atomic clocks have been getting better ever since that first cesium clock at NPL. They've just been getting better all the time. And they stalled at a huge improvement over the original performance, which was about a part in 10 to the 8th. They stalled at about a part in 10 to the 14 because of the motion of the atoms. And I'm very pleased to have had something to do with laser cooling that addresses this problem and improve the performance to parts in 10 to the 16. So here is a picture of the first fountain clock at NIST in Boulder. There's Don Meekhoff and Steve Jeffords, and they cool cesium atoms down here and shoot them up through this tower about a meter high. They come back down after a second, and that low velocity at which these atoms are moving, the long observation time that they have, allows these clocks to be good to a part in 10 to the 16th. It is the most accurately measured quantity in the International System of Units. So here's a very important idea of what was going on. We originally had time that was produced by what is essentially an artificial artifact, the Earth. There's nothing special about the Earth other than the fact that we live on it. And it wasn't good enough. It wasn't constant enough for the kind of technology that existed. And so we changed the definition to a constant of nature, a quantum transition in some atom, in this case, cesium. This is a story that we're going to see again and again. But I do want to point out that these guys, Kelvin on the left, Maxwell on the right, already understood that this was the way to do it in the 19th century. Maxwell wrote that if you wanted a standard that was any good, it should be based on the property of atoms. Now think about this. This is at a time when not everybody even agreed that there were such things as atoms. And that he says such a standard would be independent of any changes in the dimensions of the Earth, and it should be adopted by those who expect their writings to be more permanent than that body. I thought that was a wonderful bit of wry humor, that he was imagining that that scientific writing might last longer than the Earth itself. But certainly if you wanted it to be understood what the units were, he had the right idea that an atomic standard was the right thing. So before we go on, I want to offer an opportunity to ask questions. And I've even suggested some possible questions if you can't think of your own. We got anything from anybody?
Yeah, so some are coming in right now. While they're coming in, maybe I'll ask a question that's
Sure.
sort of maybe a little philosophical, but you know, I think we've all heard this sort of quote that if you want to measure something, you should always measure a frequency.
Yeah.
And as you've shown, you know, kind of we've gotten very, very good at timekeeping. Why is that? Why are we better at measuring time than other things?
That's a really good question. Maybe it's because, at least in part, and you know, it's interesting because I've had lots of questions over the years, and I haven't had that one, and so I don't really have a good answer ready. But it's a great question, and I'm wondering if part of it is that atoms are such wonderful sources of stable frequencies, and that you can do better simply by going longer. That's one of the greatest things about measuring frequency is if you just do it for a longer time, it almost automatically gets better. Now, you know, not always, and there are limits to how long you can wait. I mean, there's a thing called 1/f noise that prevents you from getting better and better and better, but we're getting better and better at getting rid of 1/f noise. But still, there is a limit to how far. But, you know, these clocks get better at times of weeks or even months as you go longer. So that's pretty good. So maybe that's the answer, but it's a great question. I wish I had a better answer.
So we've got a question from David Nesbitt. What type of clock in early 1900s was good enough to sense the slowing or the changing of the Earth's rotation?
Yeah, well, there was a thing that David actually ought to know called the short clock. It had two T's. It wasn't short because it was short, although it was relatively short as a pendulum clock, but it was named after the guy who invented it, I guess. And this was a pendulum clock that it was extremely carefully designed so that it kept a very good a very good time. In fact, it was a master-slave arrangement where you had a master clock that only synchronized the slave clock, and then you read out the slave clock. So that's a pretty modern approach to things, and that clock could already tell that the Earth was changing. I think that people who made really good pendulum clocks already understood this, and just thinking about astronomy, they understood that the day changed during the year. But it didn't take too long after that before we had quartz clocks. But the first thing was this really wonderful pendulum clock, and there's one in the NIST museum right outside the library. So if you ever visit NIST, go and look at the short clock.
So maybe we'll do one more question before we move on, and we can save some more for the next break. So Lindsay LeBlanc asks, why is a heavy atom used as a standard? Aren't there fewer corrections in smaller and simpler atoms, like, say, hydrogen?
What a great question. So when the cesium atom was chosen, there were a number of good reasons. One being the heaviest of the stable alkalis, forgetting about the fact that rubidium is radioactive. But lighter anyway. It has the biggest hyperfine separation. So having a bigger frequency is a good thing, because things like magnetic effects are going to be more or less constant, and that makes them less of a problem if I've got a higher frequency. Cesium also has a pretty high vapor pressure. As anybody who makes cesium cells in the lab knows, you don't even have to heat it up, or hardly at all, to get a decent vapor pressure. So that means it's easy to use, and since you don't have to heat it up, the atoms aren't going as fast. And because the cesium atom is heavy, that means that for the same temperature, the atoms aren't going as fast. And here's something that we don't even think about today. Cesium was really easy to detect. There's a process called surface ionization, where when something that has a very small ionization potential, like cesium, it's at the lowest ionization potential of all the alkalis, when it hits a surface that has a big work function, then that metal surface, say something like tungsten, will suck the electron off of the cesium atom, liberating an ion and producing a current if you make a circuit out of this. So it was easy to detect with pretty high efficiency cesium atoms. Today, we just shine a laser on things and scatter photons. But back then, in 1955, being able to detect something was a big deal. It turns out that cesium is one of the greatest atoms to laser cool. You can get it colder and to lower velocities than any of the other atoms. And the only bad thing about it in today's world is that it has bad collisional effects. And that's just bad luck. Rubidium's a whole lot better. So there was all these reasons that still turned out to be pretty decently good in the modern era.
Great. I think maybe we can move on for now, but we've got some more questions building up for the next break.
Okay. So next, things get even better. A short history of length. Time was important, but length was really important, because length had to do with money. People bought and sold things in length. People built things having to do with length. And the earliest standard of length was the human body. A foot was a foot. A yard was the distance from your nose to the end of your finger. Now, that was convenient, but not very consistent. If you wanted to buy fabric in the marketplace, if your short fabric merchant measured it out, you might not get what you wanted. So one approach to this was to use a particular body as the standard, the king or the pharaoh. Ancient Egypt created a thing called the royal cubit. And this is a realization of the royal cubit. They measured the pharaoh's forearm, and they made a piece of granite, an artifact. Because it wasn't very convenient to use the pharaoh's forearm, they made an artifact, okay? And we're going to see this feature come about again. And then they used that as the primary standard of length in Egypt. And when people were out in the field building the pyramids, they used secondary standards made out of wood, and they had to calibrate them against the primary standard every month on pain of death. These guys were serious about metrology, and the result was the pyramids were really, really good. Well, this idea of having artifacts became pretty widespread. All over Europe, in the town squares, there would be that town's standard of measurement. Here is the town of Regensburg. That's a fathom, and you can see that it's a pretty good length fathom. So this is probably a good place to buy fabric. But if you were to go into the surrounding towns of Bavaria, you would have a different standard of length. This was really annoying, but really common. And so here's where the French Revolution comes in. The French revolutionaries figure they're going to fix this. They're going to come up with a standard that is going to be good for all time, for all people. So they said this new standard of length that we're going to call the meter is going to be 1/10,000,000th of the distance from the pole to the equator along the meridian that goes through Paris. Of course, it goes through Paris. And what they did was they sent out teams of surveyors to survey the distance from Paris up to, I forget where it was, Dunkirk, I think, and down to Barcelona. And then they extrapolated for the whole Earth. They had a pretty good idea what the shape of the Earth looked like. And that became the new standard of measurement. They came back, they said, this is what we measured based on the old units, and this is going to be the new unit, and this is going to be the unit for the whole country. None of this town-to-town thing. The idea was something that was good for all time and for all people. And you see in this coin, this metal that they cast, we have this mythological angel actually measuring the earth. This seemed like it fit the democratic ideals of the French Revolution. There was something that available to everybody. But it turns out it wasn't all that easily available because it wasn't that easy to make this measurement. So it was just like with the pharaoh. You didn't have the pharaoh around. You didn't have the, he might even die. You didn't have the ability to measure the earth anytime you wanted, so they made an artifact. And here is a picture of the meter of the archives, a platinum bar that was deposited in the archives of Paris in 1799. Very much in this ancient spirit and very much a modern way of doing things. So that was the meter of the archives. And a little bit later, well, 75 years later, we had the International Treaty of the Meter, where the countries of the world gathered together and agreed to adopt the metric system and agreed to make a new meter. And this meter was not an end standard like the old one. It was a standard called a line standard that was the distance between two scratches on this platinum iridium bar. And this thing was deposited in a vault in Sèvres, right outside of Paris, as the standard of length for the entire world. Now, 1875 in France, people had understood, especially in France, that light was a wave, and they were already making interferometers. Here's a cartoon of a Michelson interferometer. The idea here is, well, you all know what a Michelson interferometer is. If we move this movable mirror by 1/4 of a wavelength of light, which is less than 200 nanometers, then this interference pattern is going to change from dark to light. So that means that they can measure with an interferometer something that is a length to a precision of a good bit less than 100 nanometers. And they're trying to compare this to a bar on which there are scratches. Where is the center of the scratch? You use a microscope to look at it, but even there, you can't resolve it to better than about a micron. And this interferometer can measure things to certainly better than 10 times that, and you don't even know where the scratch is. So almost immediately, this definition of the meter is inadequate for the technology of the time. It took them, again, I think this is the conservative nature of the international metrology community. It took them until past the middle of the next century before they redefined the meter in terms of the wavelength of light. So the light from a krypton lamp seemed to be very pure, and they defined the meter as being a certain number of wavelengths of the light from that krypton lamp. Here's a picture of such a krypton lamp. 1960 was the year the laser was invented. And it wasn't long before people realized that the purity of the light that comes from this krypton lamp was nowhere near the purity of the light that they got from lasers. And when they started measuring things with lasers, doing interferometry with lasers, they found that they could get much better results because the light was so pure. And people started using lasers like this. This is a helium neon laser that's stabilized to a molecular transition in iodine. And this became the de facto standard of length because it was so much better than krypton lamp. Whereas things like kryptonium lamps become the de facto standard length, so much better than the meter bar. And so it was clear that you had to redefine the meter. And the obvious thing to do would have been to redefine the meter in terms of the iodine stabilized helium neon laser, because everybody, that would have been the obvious, more brilliant minds on, and they didn't do the beam to the light. The new distance that light travels in vacuum during a certain time, there's that time and speed of light in meters per second, right? This definition of the meter, this to be the speed of light, universal relationship. Length, and you had a ruler.
Hey, Bill, I'm just gonna cut it for a second here. It looks like you're cutting out a bit. Is your Wi-Fi? Are you on solid line, or are you on Wi-Fi?
I got a little. I flashed up a note that said my Wi-Fi was not good. I'm using the NIST Wi-Fi. It's supposed to be fantastic.
Okay.
Look, you know this perfectly. What should I say that was missed? We'll try to go on. I don't know what else I can do, actually.
Yeah.
Am I okay now?
You do seem better now. Yeah. How about let's see how it goes from here, and if it seems problematic.
Okay, stop me, and then I'll stop sharing and see if I can switch. But boy, you know, I haven't even tried this new computer on an Ethernet connection. It would probably take me 5 minutes to get it up on Ethernet, so I'm a little bit leery of that.
If it continues, we can also turn off your video, and that might help.
Yeah, that might help. Okay. Anyway,
so the beginning of this slide was where it began to be really problematic.
Okay. So anyway, the key thing here is that they redefined the meter in terms of how far light travels in a certain length of time, and that definition effectively defines the speed of light, because this number here is the speed of light in meters per second. The reason why this makes it work is because by this time, 1983, people had learned how to measure the frequency of light. We've now defined the speed of light. That means that you know the wavelength of any light for which you have measured the frequency. And once you've got the wavelength, it means you can use an interferometer to measure length using that light. So the beauty of this is somebody figures out a new way of measuring frequency of light. Somebody figures out a new way of making a laser that's better. You don't have to change the definition. And these guys did that, right? Jan Hall and Ted Hench both figured out how to make better lasers, and they figured out how to make frequency measurements better. And so their improvements in this technology are immediately incorporated into this definition of the meter. So the beauty of this is that not only did you go from an artifact, a meter stick, to a constant of nature, an atom, and the light that comes from that atom, we go to a fundamental constant of nature. And the beauty of that is that we don't ever have to change again. Unless something really strange happens, I don't expect the definition of the meter to ever have to be changed from what it is right now. And this is really what I consider to be the first beautiful definition, something that depends upon not just a constant of nature, but a fundamental constant of nature. And on the 20th of May, 2019, we brought this same kind of beauty to the kilogram, and for that matter, to the ampere, the Kelvin, and the mole. And the next part of the story is to tell you why and how, but let's stop for questions about things so far. And it could go back to time as well as to what I've told you about length.
So Amir from the audience asks, what is the effect of having exact definitions of units in physics and chemistry? Why is it so important?
Well, the example that I just gave, I don't have to change the definition again when the technology gets better. In the past, I made a krypton lamp. And then it turned out that that krypton lamp, not only was it broadened, Doppler broadened, so it was hard to tell where the center was, it actually had two components because of the structure of krypton, and the shape would change depending upon the conditions under which you used the lamp. And so it was clear that wasn't going to work. You had to have something else. And if that something else had been a laser, that would have been obsolete as soon as people like Jan Hall and Ted Hench started making Hertz-wide lasers. This definition meant that new technology did not mean that I had to change the definition. So I could use that definition forever.
So
I hope.
So maybe I'll ask a related question, which is that it seems like in the story you've been telling us, the redefinition of units, as you said, these standards institutes are kind of conservative. The redefinition seems to lag behind the newest capabilities and technologies for defining new and better units and new
Absolutely.
Is this going to keep happening? Do you think? What's the next big?
So the next unit to be redefined, and I might even, if I've got enough time, talk about it toward the end of this lecture, is going to be time itself. Because right now we have optical frequency standards done by people like Junyi and Anna Maria Ray that are good to a part in 10 to the 18. In fact, I've got that on the slide. But the definition is still cesium. So that means we are 2 orders of magnitude better with what we can do for frequency standards than what the very definition of the second is. So guess what? People are starting to use a transition frequency to the metastable state, the forbidden transition in strontium, as well as other things, starting to use those as de facto standards. They're reporting measurements of frequencies in terms of the strontium frequency, for example, because reporting it in terms of cesium isn't really giving the reader the best information available. So, but when is this going to happen? My guess is at least a decade from now. Because, which is better than what we've seen historically, which is like half a century. But of course, we've had these optical frequency standards for a while. It's not like they were just yesterday. And what's going to have to happen? Well, we could talk about that later if we have time.
Great. So maybe one more question. Alexander Kermita asks, how do we know that C is constant since the Big Bang?
Right. No, that's a very good question. It's illegal for it not to be. Because remember, what we've done is we defined the meter in terms of the speed of light. Now, we, of course, had to define the second too. But the second, the frequency of cesium cannot change either. It would be illegal. What I like to tell, like when I give a talk at a school, I tell people that if they did a lab recently, which means since 1983, in which they measured the speed of light, they were breaking the law. Because you cannot measure the speed of light. It's a defined quantity. So, I mean, I realize it sounds crazy. and sometimes it's a little hard to swallow this, but we have defined C. It cannot change. Now, later we'll talk about constants that can change, but let's leave that as a teaser.
Great. I think that's a great point to move on.
Okay. So now we go to a light history of mass. So, as you would expect, in ancient times, people had artifacts, mass standards. Here's a set of stones from ancient Babylonia that have been polished, and these were the standards of mass for Babylonia. Well, I'm not sure whether it went the whole empire or whether, it was just in certain parts, but anyway, these were objects. One of these things is a shekel. I forget which one. But the problem again is that from place to place, you might have different standards of mass. And so our friends, the French revolutionaries, figure they're going to fix this problem too. And they're going to fix it using the meter, because the meter is supposed to be the measure of all things. So they come up with a new standard of mass called the kilogram. And the kilogram is the mass of a liter of water. And a liter is just a cube of water with, a tenth of a meter on a side. So this is the new standard of mass. Trouble was that while it's great in the sense that it uses the meter, that's wonderful, and it uses water, which is pretty readily available, it wasn't that easy to measure out 1 liter of water. Water wets things, water changes its density with temperature. So it turned out that you could weigh things to a higher precision than what you could determine what a kilogram was. So what did they do? What they always did. They made an artifact. And here it is. This was a real thrill for me. I'm holding in my hand the thing called the kilogram of the archives, a platinum cylinder made to be as close as they could make it to the mass of a liter of water. The other thing is water has a density of, 1 relative, to platinum has a density of about 23. So the buoyancy correction is horrible if you use water, not to mention the fact that it's evaporating while you're measuring it. Anyway, so they made an artifact. And I'm actually holding the box that holds that 1799 artifact that was the kilogram of the archives. And this is the new kilogram that they made in 1875. They made another copy, this time out of platinum iridium, just like the meter rod. And there it is. That is, and was until 2 years ago, the standard of mass for the entire world. It was the last artifact. It was made to be as close as possible to the kilogram of the archives, and it became a kilogram for the world. That's the definition of a kilogram up until 2 years ago. Think about this. We are in the 21st century on the 19th of May, 2019. The definition of the kilogram, the unit of mass for the entire world, is an artifact, a piece of metal that was made in the 19th century that was based on an artifact made in the 18th century. This is absolutely scandalous that in the modern era we would have such a situation. Imagine if somebody left a fingerprint on the international prototype of the kilogram, all of you would lose weight. We cannot have that. That's just intolerable. Well, nobody leaves fingerprints. They handle it very carefully, but its mass is changing nevertheless. Here is a plot of the mass of a bunch of different copies made at the same time in exactly the same way as the international prototype of the kilogram, measuring it, like 3 times since it was made, or maybe 2 times since it was made. When it was made, they measured them, and then since then they've measured them twice on this graph. They had another new measurement before the redefinition. Anyway, the point is that it looks like they're all drifting in the same direction. Now, if you think about that for a little while, you might imagine maybe it's the international prototype of the kilogram that's drifting. Okay, they're all drifting. And what's the constant mass? There is no way of knowing, because the definition of mass is that object. By law, it cannot change. It is always a kilogram. And you know damn well, just looking at that plot, that it's not constant. So we got the same situation that we had before. What do we do? And the answer is we're going to do what we did with the meter, this beautiful definition of defining a fundamental constant of nature. So what are we going to use? Well, probably probably a lot of you already know, but let me remind you of the most famous equation in physics, right? What does this mean? It means that the total energy of an object at rest is equal to the rest mass of the object times the square of the speed of light. Great equation. We all love it. Here's another equation that physicists love almost as much, not as well known by the general public, that the energy of a photon is Planck's constant times the frequency of the light. Now let's combine the two equations and solve for the mass. Now, what does this even mean? The mass on this side of the equation is, or at least I think of it as being the change in the mass of an object that emits a photon that has this frequency. So you see what happens. If I measure the frequency of that emitted photon, and I've defined the speed of light, and if I now define Planck's constant, I know what the mass change is in kilograms. Now, it turns out we don't actually do it this way. I mean, you can weigh photons this way. We just can't do it well enough yet to be suitable for being a mass standard. So instead, we have an electromechanical device, and this is what I spent, about the first 10 years of my career at NIST doing, invented by this genius, Brian Kibble, and I'm going to now show you how this works. So first, I want you to remember how we measure mass normally. The way we normally measure mass is we got an unknown mass here, and we start putting known masses, things that are related to the international prototype of the kilogram, on the other side until it balances. We've all done this, right? And when the whole thing balances, then you know what the unknown mass is. And it's got all the problems that we've just talked about. Now I want to invite you to imagine a different way of doing this same problem. What we're going to do is we're going to, instead of putting on this side of the balance masses, we're going to put a coil of wire and a permanent magnet. And now what I'm going to say is that this coil of wire, if I put in a known current into that coil of wire, and if I know what the magnetic field is and where it's pointing, how strong it is everywhere that there's wire, and I know where the current is going in the wire, and I'm going to tell you right now, we have no way of doing all that to a sufficient accuracy. But if I could do all those things, then this would give me another way of measuring mass, because I could calculate what the force is if I knew all that stuff, and then I just measure the acceleration of gravity and to mass, and I'd be able to measure the mass. I can't do it because we can't do things like measure the magnetic field and its direction to a sufficiently good accuracy. So here's where the genius of Kibble comes in. What Kibble said was, yes, we can't measure that. Let's do something else that we can do. Take that coil of wire, open up the coil, and take the leads of the coil and connect them to a voltmeter. And now move the coil in the field of the magnet. And whoops, oh, damn. Now I got to go back and I don't know why that happened, but it's just probably because okay, great. So now if you move a coil in a magnetic field, you generate a voltage, right? And you measure the voltage and you measure the velocity coil using an interferometer. Then you do the other experiment that we already did. We call this the velocity mode, where we measure the voltage and the velocity. And then there's the other mode, which we already talked about, where you just measure the force compared to the mass on the other side of the balance. We don't try to measure we measure the current in the coil to produce that force, but we don't try to measure the magnetic field, okay? We just measure the current. Now, here's the beauty of it. If we take the mass we had from the weighing mode, multiply it by gravity, which we just measure separately, multiply it by the velocity from the other experiment, the thing we call the velocity mode, that has got to equal the current that we measured in the weighing mode, whatever balanced this force over here, times the voltage that we measure from the velocity mode. Why? Because mechanical power has to equal electrical power, and force times velocity is mechanical power, and current times voltage is electrical power. things have to be equal. So we solve for the mass, and we find that the mass is equal to the current times the voltage divided by the acceleration of gravity times the velocity. And we can measure those things well enough. Now, you might say, wait a minute, you told me this was Planck's constant. Where does Planck's constant come in? And Planck's constant comes in because we have a quantum way of making electric measurements. The quantum Hall effect from Klaus von Klitzing and the Josephson from Josephson. So here's Brian Josephson. He gave us the Josephson constant 2E over h, which is measured in hertz per volt. So if I measure a frequency in an AC Josephson junction, I'm going to get the voltage across the junction. Klaus von Klitzing gave us the effect, a transverse resistance measured in ohms in terms of h over e squared. If we plug in the unit that we are going to measure the voltage and the current in, then we're going to find that the current is proportional to E, as you might expect it to be. And when we solve for the mass, with the voltage being proportional to h over 2E, we find that the mass is proportional to Planck's constant, which is what I promised you. Here is a picture of such a balance, the real thing, at NIST. This thing can measure kilograms to a part in 10 to the 8th, which is better than what we see the kilograms changing by because of whatever it is that's causing it to change, which we don't know because we can't figure it out because we don't have a stable standard of mass. Now we do, and maybe we'll figure it out. Here is part of the team that did it. These people were so confident in their measurements that they tattooed the new values of the fundamental constants on their arms. These people were as serious about metrology as those ancient Egyptians. There it is. And those are the values of Planck's constant, the charge in the electron, the Boltzmann constant, and Avogadro's number that were all changed on the 20th of May, 2019. So let's stop for questions here before we go to the final bits.
Okay, great. So we got a question from YouTube, actually, from a user called The Safe Disaster. Not sure who that is, but are there any issues expected in the future with defining these constants for measurements within terrestrial labs that inherently are in non-inertial frames?
Yes. So one of the things is that mass is how shall I put it? Okay, forget that I said that. I don't know what I was thinking. Frequency. A frequency source is redshifted when it's deeper in a gravitational potential. So take something like a cesium atom, our present standard of frequency and of time, and therefore of time, and think about measuring its frequency in Germany, which the PTB is close to sea level, and in Boulder, Colorado, which is 1.5 kilometers above sea level. Those frequencies are not going to be the same. They are, remember, when you're in a gravitational field, it's the same as if you're in an accelerated frame. So it's non-inertial in that sense. It's also non-inertial because you're on the Earth and the Earth is rotating and all those kinds of things. But at least that part is almost the same between those two places. But it's not easy to determine the difference in the gravitational potential between Boulder and sea level. And the definition of time, which you don't see in the short definition, but if you have the full, what's called mise en pratique, the putting into practice of the definition, it specifies that the time is at mean sea level. Now, talk about the future. What is mean sea level going to be with global warming? How is the redistribution of mass from the polar ice caps to the rest of the world, raising the sea level? How is that going to change the way in which cesium clocks work? So these are real questions that people are thinking about now, and we don't really have the answers to them, but we are already taking account of the fact that Boulder is different from Braunschweig or from Teddington, or from Paris because of the gravitational potential. So we know how to make that correction. We just don't know how to measure the difference in gravitational potential between those places. People are turning the whole thing around and using clocks to do geodesy, to measure the gravitational potential by measuring the way in which the clock rates change. So it's really a lot of fun. And the future isn't entirely clear at the level of parts in 10 to the eighth. Parts in 10 to the 18, which is where these things come in. Let me just tell you one very quick story. When I first came to NIST in 1978, the best clocks were in Boulder, and they were good to a part in 10 to the 13. If you'd had another clock in Washington at the time, which we didn't, and it was just as good, then the difference in gravitational potential would have implied a difference of frequencies that was just at the level of uncertainty of the clock, of the two clocks that are part in 10 to the 13. You could just tell 1.5 kilometers. Today, we can tell 1 centimeter. So that's how much clocks have improved during the time that I've been here. And I've had some little bit, our group has had some little bit to do with making that improvement possible. So maybe we should go on.
Thanks. Yeah, so we actually just lost our moderator to a connection issue as well. So maybe there are some more questions here, but let's save them to the end, like you said, and then we can sort of ask them that.
Okay, great. So now this is an AMO talk, right? It turns out that there's a more beautiful way of getting a kilogram from defining Planck's constant that's all, well, it's not all AMO, but it's mostly AMO. Imagine an atom at rest, and imagine the atom absorbs a photon whose frequency and therefore whose wavelength you know. The atom will recoil with a velocity that's given by h over m times lambda, the wavelength of the photon. It's h bar k over m. That's just what this says. By atom interferometry, you can measure this velocity. If you measure that velocity, and you know what h is, and you know what lambda is, you know what the mass of the atom is in kilograms, not in atomic mass units or something like that. You know what the mass of that atom is in kilograms. So people do this. This was pioneered by Steve Chu, but today in Paris, they're getting this at about a part in 10 to the 10th. By atom interferometry and using cold atoms and Bloch oscillations and all that. And now you've got the mass of a rubidium atom in kilograms. You can compare the mass of a rubidium atom to the mass of a silicon atom in an ion trap really, really well. And then you can make a perfect crystal of silicon, measure its lattice constant by X-ray interferometry, measure its size by optical interferometry. That means you can essentially count the number of silicon atoms that are in that sphere right there. And that allows you to get to a kilogram from the mass of an atom. So this is an alternate way. And the beauty of this definition is it doesn't tell you which way you should do it. These two techniques are about the same in their ability to realize a kilogram. I just love this one because it's so beautiful in its AMO-ness. So people all over the world have been doing this, some of them doing it by this silicon sphere technique, some of them doing by the Kibble balance. And when everybody was agreed that they had consistent values for this thing, then the International Conference on Weights and Measures decided to go ahead with the change. And this is the movie that they showed after 60 countries of the world voted unanimously to change the definition of the kilogram and the three other constants. So here it is.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world's scientific community.
At times, it seemed
impossible.
Accurate.
Precise measurements.
Anytime.
Anywhere. And
we did it.
Ce l'abbiamo fatta.
Vi haben es geschafft. Lo logramos.
Neyse Boli.
我们做到了.
Biz buna nail olduk.
Proud om die.
We worden жасадық. Het is ons gelukt.
We сделали это.
انتصرنا.
We gjorde det. My jsme to učinili. Dokázali jsme to. Congratulations. Scambila. Felicitaciones.
Congratulazioni.
Siate relevoricia. Selamat sukses. Parabéns. Ongela. Omedetou. Onneksi olkoon. Mabruk. Aiko.
Félicitations. Congratulations.
So if 60 countries of the world can unanimously agree on something, maybe there's hope for the world. But anyway, that's not the whole story. There were these other things. The charge of the electron was defined, and that defines what the ampere is, because the ampere is now a certain number of electrons per second. And similarly, the mole, which used to be the number of entities equal to the number of carbon-12 atoms and 12 grams of carbon-12, is now just a number. We've defined Avogadro's constant. And the Kelvin is now defined by defining the Boltzmann constant. So the temperature of something is now defined in terms of the energy, the thermal energy of its constituents. So it's a beautifully atomic way of understanding what temperature is. The one we carry in our minds all the time is now enshrined in the very definition of what we mean by temperature. So the French Revolution brought us the metric system. The International Meter Treaty brought the metric system to the world. And now this change of the metric system has produced something that I really think realizes the dream of those French revolutionaries, which is to provide something that's good for all time and for all people by fixing the value of the constants of nature. So now you can have the whole SI system on a wallet card, and it really looks like we've done what the revolutionaries imagined, that we've got something that's good for all time and for all people, except maybe for time itself. So thanks very much. And possible questions.
Great. Thanks so much, Bill, for exceptional talk, and in true sort of appropriate for someone talking about units and from NIST, you nailed the timing. We're right at the hour. It's very impressive. And so, yeah, there's a number of questions here. I had to move to the lab because I was having connection problems in my office, but appropriately, that means there's a strontium optical lattice clock behind me. So that's sort of
what could be better?
Exactly. So let's see. So I have to jump back and forth between screens. But so Adam asks, how do you make a perfect sphere of silicon?
Yeah. This is really something that's been a lot of engineering expertise. So the answer is that you keep working it and keep measuring it, and then if it's a little bit out, then you polish it a little bit more where it needs it. And when you they started off by machining a boule of single crystal. Not only is it single crystal silicon, it's isotopically pure. So I think it's like pure to ppm, silicon 28. But anyway, so that they keep measuring lots of different diameters, seeing what it is, and then rework it. So it took a long time to do that. But it is finally the most spherical object that has ever existed on Earth.
So let's see here. So Nathan Shine asks, in what sense is the gravitational redshift important? In that if you actually connected PTB and NIST with a fiber, the redshift would adjust the photon frequency appropriately.
Yeah, no, that's I'm so glad you asked that question, because that's what it appears to be. If you take this point of view, let's say that I've got a clock on the ground and a clock up in a satellite, for example, would be another example. Then one of the features that we that we talk about is that, well, if the photon were falling, you see, then it would pick up energy And if the photon were rising, it would lose energy. And this is one of the ways in which we understand the redshift. But since that shift occurs in the rising or falling, doesn't it cancel out? This was actually a discussion that people had when they first set up the GPS system. They weren't really sure how they should apply this feature of general relativity. And of course, the people who'd studied general relativity had a pretty good idea, but there was enough disagreement over just this sort of argument, that they had a switch in the software to either account for or not account for the gravitational redshift, which you have to get by measuring the ephemeris of the satellites. And it only had to operate for a little while before it was clear which way it is. No, there is a shift. And so you are going to see that clock as being different if you measure a satellite clock down on the ground. You see it as being different. When you're there in the lab, of course, you don't see it as being different. All the physics is the same. If it's not, then the equivalence principle is wrong. And of course, that's one of the experiments you want to do. You want to take two clocks that are on different atoms and side by side compare their frequencies as you change their position in the gravitational field. And that's a really great experiment to do in a satellite that has an eccentric orbit. So it's a really important thing to do, because it'll tell us whether this aspect of the equivalence principle is right or not, and be able to test it at a level that's never been possible before. So, but this is a really important question.
So maybe we'll take one more question. So Lindsay LeBlanc asks, a lot of these measurements rely on the fact that atoms are identical particles. I think we know this very well, but is there any possibility that they are not? Are there any implications if they are not identical?
Yeah. So if they aren't, there are implications that go well beyond the problems of metrology. So if, for example, two rubidium atoms were not the same, then the vibrational spectrum of rubidium dimers would be different, because you can't have certain rotational states because of the fact that the rubidium atoms being bosons, have to have their total wave function has to be symmetric under interchange. And that means that certain rotational states are not allowed. It's just like two bosons at low energy can't have p-wave interactions if they're in the same state. It's more of a problem. Fermions, like two potassium 40 atoms, can't have s-wave interactions if they're in the same state, because if they did, they would be they'd have an overall wave function symmetric, and it has to be antisymmetric. So by the same token, you all know that, or a lot of you know it, because that's why you caramelize a gas of fermions that are all in the same state, because they don't have any s-wave scattering. And s-wave is all there is at really low energy. By the same token, you couldn't have two identical fermions in rotational state of a molecule that was even, because that would, if they had the same internal state, because that would create a symmetric function. So it would have huge implications. You would be able to see states of, I hope you can hear me, because I'm getting the indication now that my internet is unstable again. But anyway, so you would see molecules that shouldn't exist. People have looked for these. Like, are there a few rubidium atoms that aren't that aren't identical? I think that if there was anything about rubidium atoms so they weren't identical at all, that in other words, that it made them boltzons instead of bosons, then we would have seen that already. But what if there was some brand of rubidium atom or strontium atom or whatever that was not identical to the others, that had some quantum number that we haven't discovered yet, and they were rare, and everything else about them was the same, except maybe the frequency was just a little bit different? Well, people have looked and haven't found them yet, but when you're looking for something that's rare, you don't know whether you're going to find it. The thing I find intriguing, along with that, it's a great question, Lindsay, is how did Maxwell and Kelvin know that the atoms were all the same? We understand that as being a quantum mechanical feature. How did they know?
I think that's a great note to end on. So we'll thank Bill once again for a really fantastic talk and for being kicking off the new season of Vamos. And on that note, I'm going to take over sharing screen here for a minute to show you the upcoming seminars. So hopefully you all can see this. So in 2 weeks, on September 24th, the Vamos talk at the same time, same place, same link and everything will be Tim Tamignow from TU Delft. We don't have a talk title yet, but he'll be telling us about sort of clusters of nuclear spins in NV centers for quantum information science. And the quantum science seminar has been on summer break as well. My understanding is they'll be coming back on the 23rd, the day before the next Vamos, but they have not yet announced their new speaker. And so we'll end there. We're gonna put the links to the informal discussion with Bill. It'll be a separate Zoom room and it'll be a Zoom meeting, so you'll actually be able to interact with him face to face. And thanks again, once again, Bill, for a really great talk.
You're most welcome. That's going to be now in the chat. Is that?
Yeah.